Today we're going to start looking at properties of logs. Now, as you remember hopefully from Algebra 2, a logarithm is really the inverse operation of an exponent. Now, logarithms were actually invented before calculus by a man named John Napier, I think in about 1610. So he was an Englishman, and what they were looking for is ways to solve exponential equations when you couldn't get the base the same. Now, because every function has an inverse, we call the inverse of an exponential function the logarithm. And basically a log looks something like this: y equals log some base with x, where b is the base. Now, we have two types of bases that we deal primarily with in math. We have what's called the common base. Now, you may recall that the common base is base 10. We write these as just y equals log of x. We also have the natural base. And again, you may recall that is base e. And we write that very differently. We write this as y equals the natural log of x. And there we have our log equations. Now, the first property we're going to talk about today and deal with is what's called the inverse property of logarithms. This is what we use to solve logs. This gives us the relationship between logarithms and exponentials. And it basically says this, that if the log base b of x equals y as an exponent, then we can say b to the y equals x. So this is the logarithmic form of an exponent. Now, this is a very important formula, and you will need to have it memorized. But we're going to do enough examples so hopefully it will help. Now, because exponents and logarithms are inverses, they are considered equivalent functions. So we can use either the logs or we can use the exponents and to help us simplify. Now, so let's take an example. We want to simplify this, log base 2 of 32. So what we're going to do is we're going to convert to an exponent. So to convert this to an exponent, I'm going to rewrite it, log base 2 of 32, and I'm going to set that equal to some number, some letter, I don't know what it is. We'll call it A. Now, this is the log form. To convert it to exponential, we look at the base 2, and we're going to raise that to the power of A. And that's going to equal the 32. And that's our rule up here. B to the y equals x. And now, hopefully, remember, we can actually solve this one because 32, if you remember, is just 2 to the 5th. Let me check that out. 2, 4, 8, 16, 32. Yep. So therefore, we know A is 5. And as a result, the log base 2 of 32, what's that going to equal? 5. So let's try a couple more of these on our own. Let's try a couple more of these. Log base 4 of 2. I want to simplify this if we can. Set that equal to some unknown value. We'll call that A, and we raise our powers. 4 to the A equals 2. Now, I can simplify this because, remember, 4 can be written as 2 squared, so that's 2 to the 2A equals 2. Be careful, there's a 1 there. What does A equal? 1/2. And you should be able to do that in your head. Very easy. Now, be careful with number 2. This is our common log. Okay? It's a common log. Now, so when I set this one up, the base, even though it doesn't say a base, we can make it a base of 10. So we're going to write this as 10 to the A equals 1 over 100. And now, a little bit tougher, but I want to write this as a common base now. See, I have one rule for logs. It's like Fight Club. What's the one rule for Fight Club? Don't talk about Fight Club. The same thing with logs. I have one rule for logs. Don't work with logs. We convert them to exponents. So we're going to get 10 to the a, and I can flip this. This becomes 10 to the negative 2. Because if I flip it, it becomes negative, and of course 100 is just 10 squared. So we're going to get a equals negative 2. Very easy to do. All right, let's try number 3. Ooh, this is a hard one. Let's put a splat on this one. Set that equal to a. We're going to get 3 to the a. And what's that going to equal? 1. Now, for most part, most of us could probably kind of reason through this one. What power on a is what's the only thing we can make a that will make that a 1? And of course, the answer is 0. But what I always tell people is this. This is the universal base. It's the universal base. So I'm going to write this as 3a, and this just becomes 3 to the 0, because 3 to the 0 is 1. I just write it as the base of 3. So a equals 0. So next time you're in a fight with somebody and you're in a verbal spar, you say, you know what? I may be a lot of things, but you are the log base 3 of 1, because you, sir, are a 0. And just watch them cry home, because you can't get any lower than that type of insult. All right. Oh, no, here's number 4. They're using a. Mr. Wernow, what do we do? Pick a different variable. Let's use x. So we're going to go a to the x equals a squared. What does x equal? 2. Now, there is a rule for this one right here. There is a rule for here, okay? And I'm going to show you this one. The log base b of b to the x is just x. If they have the same bases, they cancel. And that's our rule. The same bases cancel. And when we come to solving equations, that's going to become important for us later on, especially when we do exponential equations. All right, let's take a look at number 5 here real quick. Set this equal to a. Again, this is our common log, base 10. This is a slightly harder one. This is 10 to the a equals 0.001. And I know what you're thinking, Mr. Werner, what common base do they have? You have to think scientific notation. 10 to the a, this is 1, 2, 3. This is 10 to the negative 3. So what's a going to equal? Negative 3. All right, pause right now for a second and see if you can try number 6. Right. To work number 6, set that equal to a. We get 7 to the a equals, this becomes 7. Now, I don't like the cube root, so I'll write that as a 1/3. So a is just 1/3. Very easy to do. All right, now if you notice, 7 has kind of a splat on it, and there's a reason for this one. This one's slightly trickier. Now, there's another property we're going to talk about tomorrow. You may recall, if you are multiplying inside a logarithm, we can add. And the rule says this, the log of AB becomes the log of A plus the log of B. So I'm going to rewrite this as the log base 4 of 16 squared plus the log base 4 of 7. And I want to simplify this one. This one's a little bit trickier to do, okay? So if I want to simplify here, just work only with this one, okay? We're going to get 4 to the a equals 16 squared. Of course, we get 4 to the a equals 4 to the 4th. Now, I didn't use my smallest base because I recognize I can write 16 as 4 squared. So we get a equals 4 here. So I could rewrite this as 4 plus log base 4 of 7. Now you might be asking, why didn't I simplify the log base 4 of 7? Well, let's try that. Here we would get 4 to the a equals 7. I can't solve this one yet because I can't write 7 and 4 in terms of the same base. In order to do this one, this is where we need to solve logs. We need logs to solve that one. Now you're going to have a couple on your assignment like this one. I would definitely try number 7 once or twice more, okay? All right, go on to part 2. We're going to take a look at natural logs and another application of the inverse property.